In this section, we are discussing selection and proper use of biosafety cabinets. Now, all of us are familiar with laminar airflow units. These systems are designed to protect the culture. It is for product protection. And to protect the product, what you need predominantly is avoiding biological contamination. So, what you have here, the focus is bio-exclusion. Now, these kind of workstations are quite all right for doing non-pathogenic work, working with non-pathogenic cultures. For example, aseptic transfers, dilutions, and so on and so forth. Now, the moment you have pathogenic cultures, your requirements multiply. Biosafety cabinets are very special configuration of laminar airflow units where they meet two important requirements. One, as usual, protect the culture from biocontamination. Therefore, bioexclusion is very much part of the design. Apart from that, you need to protect the operator. You need to protect the environment. Therefore, there is biocontainment. So, bioexclusion along with biocontainment is what distinguishes a biosafety cabinet from other ordinary laminar airflow configurations. Now, there are different categories or designs of biological safety cabinets. You have them grouped or ranked as class 1, class 2 and class 3. A class 1 provides inward airflow to protect the operator, and all the air that is drawn in from the laboratory environment is exhausted outside with or without a HEPA filter, depending on the nature of the work and the risk perception. Class 2 biosafety cabinets, the worker, the product, the environment are all protected. It offers you a sterile work area, a bioclean work area. Its use can range from simple tissue culture to extremely dangerous virological manipulations. And finally, you have class 3, which is totally enclosed, it is ventilated, and it is airtight, hermetically sealed from the laboratory environment. And it is suitable for work in BSL 3 or BSL 4 facilities and risk level 3 or 4 infectious agents. Now, class 2 has different design configurations. You have broadly two groups, the A group and the B group. Type A1 and type A2 are designed to exhaust 30% of the air. That exhaust is HEPA filtered and could be returned to the laboratory environment or exhausted outside. But it is not hard ducted outside. Whereas type B1 exhausts 70% of the air and type B2 exhausts full 100%. Whatever comes into the work area is exhausted out through proper filtration. Type B1 and B2 must necessarily be hard ducted outside with dedicated exhaust fans. Now, selection of a safety cabinet through risk assessment. For BSL level 1, personal protection is given, product protection is not important, and environmental protection is certainly important. Therefore, usually a BSL 1 facility, any exhaust has a HEPA filter before it is exhausted. In BSL levels 2 and 3, you have personnel protection, product protection, and environment protection. And the kind of biological safety cabinet recommended for level 2 is either A1 and A2 or B1 or B2. BSL 4 facilities offer personal protection, product protection, and environment protection. And in these facilities, predominantly, we use class 3 biosafety cabinets. If B1 or B2 type of configuration is selected for use in a BSL 4 facility, it is invariably in a suit room where the operator is fully suited and with integral breathing apparatus fitted. Here we have a look at a biosafety cabinet type 1, which is basically similar to a fume hood, except that here you work with biological cultures or sometimes radioisotopes, but not with aggressive chemicals. For aggressive chemicals, you need a fume hood. The materials of construction should be appropriate for the kind of chemicals that you use. Biosafety cabinets are not intended for use with harsh chemicals. Now, as we look at the side view, you see the air from the room entering the cabinet. And you find that air is being drawn towards the rear of the particular cabinet through an air directing baffle. And that ensures that there is a smooth flow of air without causing turbulence, excessive turbulence in the work area. And it is drawn towards the base of the back and then drawn upwards through a HEPA filter and released to the exhaust. And usually the air is exhausted outside the building. Now, the same concept is to be used in all your fume cupboards. Now remember, a fume cupboard not only contains and exhausts fumes, it can also contain and exhaust heat to see that the heat load in the laboratory is not excessive. So wherever you have a water bath or you have any procedure that is exothermic, then you contain the heat and exhaust the heat so that the air conditioning load in the laboratory doesn't become excessive. So you have here some interesting features. You have a sash that is moving up and down. Regardless of the position of the sash, the air velocity entering the fume hood should remain constant. If a fume cupboard is not designed properly, whenever the sash is high, the entry velocity falls. And whenever the sash comes down, the entry velocity is so high that usually the flames, if any, are put off. To ensure that the intake velocity or entry velocity is constant, there's a very special design here. You can see the perforations at the top panel where there's an arrow. And there is this sash that slides up and down. When the sash is up, the perforations are blocked and the air intake is predominantly at the work table. As the sash moves down, part of the perforations are open for air and part of the air enters from there, and the remaining amount of air is drawn at the work surface level. And there is a balance between the two such that the air entry velocity remains fixed at 100 or 120 feet per minute. This is called the bypass design. As in the earlier case, you can see there is a baffle at the back towards the rear of the work surface, and the air is drawn towards the rear so that undue turbulence in the work area is avoided. Next comes a question of the exhaust ducting. As you exhaust the air to the outside, the air should be accelerated. To be able to accelerate air, the duct size progressively reduces. Since the quantity of air that is moving is equal to the cross-sectional area into the velocity of the exhaust stream. As the area decreases, since quantity is the same, the velocity increases. Please remember duct velocities should be in the range of approximately 2000 to 2500 feet per minute. So you start with a duct which is, say, 10 inches in diameter, reduces to 8 inches diameter, reduces to 6 inches diameter, and to 4 inches diameter, so that there is a progressive acceleration of the exhaust stream. Fume containment and heat containment in exhaust hoods can also be used for storage of chemicals, so that when you open the cupboard, you don't get a strong whiff of the kind of chemicals that are kept in that particular cupboard. Now please remember that whether it is biosafety cabinet or whether it is a fume containment and exhaust hood, the exhaust is very critical. The exhaust motor is very critical. Now if the motor backs up, then you could be compromising the safety of the people in the laboratory. So it is always good practice to have a redundant motor. Now if you have a redundant motor, it doesn't mean you just have that motor and leave it there and hope that on one day when you need it, it will work. So you should keep on operating one motor for half an hour, then this switches off, the other motor takes over, then that works for half an hour and then this takes over. So both of them are kept in constant operation. You should be alternating between the two exhaust motor blowers. Secondly, if the power fails, the motor may stop and till a generator takes over. You cannot afford that backflow. You cannot afford idleness in the exhaust duct. Therefore, it's always good practice to ensure that your exhaust motors are always connected to an UPS. And if there is main power, it goes through the UPS to the exhaust motor. And if the power fails and the generator takes over, the UPS makes sure that the exhaust motors continue to run. There has to be an alarm to indicate that the exhaust motor is in trouble. If it fails, you should know about it immediately. This is very important, regardless of whether you're talking about a biosafety level 1, 2, 3 or 4. As long as it is a fume hood or a biosafety cabinet and exhaust is a critical element, then you must give it the necessary attention. Here we have what is called a type A1 biosafety cabinet, the kind of cabinet that all of you are familiar with. You have a motor blower at the bottom below the workbench, and air from over the work surface passing over the cultures and therefore getting contaminated is drawn downwards into the blower. Part of the room air is also sucked in through the perforations in the front of the work surface. The air from the room as well as the air that is swept over the work surface are mixed together, and this contaminated air is pushed upwards to the plenum on top, where part of it is returned to the work surface through a HEPA filter, which is called a supply HEPA filter, and part of it is exhausted through a HEPA filter either back into the room or to the outside. Now, as I said earlier, in type A1 and A2, 30% of the air is exhausted, only 70% is recirculated. Type A1 biosafety cabinet, the entry velocity or the face velocity of room air entering the cabinet work surface is a minimum of 75 feet per minute. The other distinguishing feature about type A1 is that there is a duct connecting the blower to the plenum where there is a supply filter and an exhaust filter. That connecting duct is contaminated and under positive pressure. Now, as I said, the air from the biosafety cabinet, which is being exhausted through a HEPA filter, could be released back into the laboratory so that the air distribution in the laboratory is not disturbed. But if you wish to exhaust this air to the outside, then you don't hard connect the duct. What you do is use a kind of a cap. It is called a thimble unit. And that cap does not touch the biosafety cabinet. It is approximately 1 inch away from the exhaust HEPA filter. That is, the gap between the exhaust HEPA filter and the thimble unit is approximately 1 inch. So that room air is sucked in along with whatever is coming out of the biosafety cabinet, and the two of them are mixed and taken to the exhaust duct. Now, type A2 biosafety cabinet, like the type A1, exhausts 30% of the air and recirculates after refiltration 70% of the air. Now, what distinguishes this from A1 is that the entry velocity, face velocity of the room air entering the cabinet is not 75 feet per minute, should be at least 100 feet per minute. Secondly, you find that there is no part of the system where there is air that is contaminated which is at positive pressure. All contaminated ducts are under negative pressure. This means if there's any leak in the duct, room air will get sucked into the duct, but the contents of the duct will not leak into the room. It is because of this that type A1 is now being discouraged for biosafety work, because there is a duct connecting the blower below the work surface to the plenum above the work surface, and that part of the duct is contaminated and under positive pressure, something that the safety experts are increasingly wary about and have now categorically discouraged that design for biosafety work. So type A1 is as good as non-existent for biosafety environments. You need type A2 at the very minimum. This is for work with infectious agents, usually at risk level 2 and seldom for risk level 3. The exhaust air could be released in the room, as in the case of type A1, or with a thimble unit exhausted to the outside. Biosafety Cabinet Class 2 type B1 comes in two versions. One is the standard version, which has got a work surface, a HEPA filter below the work surface, so that as soon as the air is contaminated with the cultures, the HEPA filter filters it out and renders it clean. This cleaned air is taken up above the work surface to the plenum, where there is a supply HEPA filter and there is an exhaust HEPA filter. So no contaminated duct is under positive pressure. The duct connecting the blower at the work surface bottom to the plenum above the work surface, that duct is not contaminated. The air has been filtered out. It is bio-clean. In B1, 70% of the air is to be exhausted out and only 30% is to be recirculated. And it is usually meant for pathogens slightly more dangerous than that used in type A2. It could be risk level 2, it could be risk level 3. The velocity of air entering the work surface should be 100 feet per minute, and the exhaust should necessarily be hard ducted to the outside with a dedicated exhaust motor blower assembly system. Now what we see here is also a B1 type with 70% exhaust and 30% recirculation, very similar to the one we saw earlier. The earlier one was a standard floor standing version, but this is a tabletop version. The floor standing version had 3 HEPA filters, one below the work surface, one above the work surface, and one exhaust. And here you have only 2 HEPA filters, the supply HEPA filter and the exhaust HEPA filter. Now, although the air is being drawn through a duct from below the work surface, which is totally contaminated, and being drawn upwards or pulled upwards by the blower above the work surface, therefore, that particular duct which is contaminated is under negative pressure. Should there be any leak, the room air will rush into the duct, but contaminated air will not come into the room. Here we have the last of the Class 2 biosafety cabinets, type B2, where 100% of the air is exhausted. No air is recirculated into the workspace. Air is drawn in, part of the room air enters to ensure that the work area is under negative pressure with respect to the room. The entry velocity of the air entering the cabinet is 100 feet per minute at least, and the entire air is to be exhausted out. The picture that you see is a tabletop unit with one supply HEPA filter and an exhaust HEPA filter. As in the case of type B1, the exhaust has to be hard ducted and with a dedicated exhaust motor blower assembly exhausted into the outside environment. Now, in the case of Class 2 A1, the entry velocity is 75 feet per minute. That is with the sash in the open position. And in the case of A2 or B1 or B2, the entry velocity of air from the room entering the biosafety work surface edge should be 100 feet per minute. It should not be too high. It should not go beyond 120 feet per minute with the sash open up, whether it is A1, A2, B1 or B2. Now just imagine if you have a 4-foot wide table and let's say perforations are 6 inches for the air entry from the room into the cabinet. Now it is perforated, it is not open. It's not the amount of space available for air to enter is not the full 6 inches. It's only a fraction because there is the work surface interfering with airflow. So depending on the kind of perforations, the effective air path, assuming the area is, let us say, 4 feet wide by 6 inches, you would imagine that the area available is 2 square feet. But the full 2 square feet is not available because of the work surface that hinders the airflow. So depending on the size of the perforation, the effective air path may be 20% of the air area or maximum 40% of the area. So even if you have 4 feet of width and 6 inches of depth available on the work surface with perforations for the laboratory or workplace air to enter the cabinet, you have, because of the perforation, the effective area available for the air to enter is not 4 into half, that is 2 square feet, but about 30% of that area. So around 0.6 to 0.7 square feet is the effective cross-sectional area in which air is entering, either at 75 feet per minute as in the case of A1 or at 100 feet per minute in the case of A2 or B1 or B2. That means around maybe 100 CFM or 75 CFM is being drawn from the room into the cabinet, regardless of whether it is A1, A2, B1 or B2. But B1 exhausts 70% of the air, B2 exhausts 100% of the air, and in the case of A2, which earlier used to be called B3, but it is now called A2. In A2, you're exhausting only 30% of the air, but still it is 30%. Now, if the air in the work area is, let us say, 700 CFM, because laminar airflow velocity is, let's say, 90 feet per minute, and you have 4 feet by 2 feet, that is 8 square feet. And 8 into 90 gives you around 720 CFM. Let's say 700 CFM. And that represents 70%. That means the exhaust is 300 CFM in the case of type A2 or A1. And if this is supposed to be 30%, the air coming inside is supposed to be 30%, then the air that is being exhausted is approximately around 1500 CFM. Now, the air being drawn from the laboratory is restricted to around 100 CFM, maybe 75 CFM maximum to 150 CFM or less. So, where is the balanced air coming from? Now, let us say we are talking about 100% exhaust, and you have 4 feet by 2 feet, and that is 8 square feet. Now, 720 CFM of air is coming in. All that 720 CFM has to be thrown out. But only 100 CFM is coming from the room. So where is the balance coming from? So for that, you have something called add air system. You take air from some nearby corridor, it need not be tempered or controlled environment. You take the air and filter it, or at least pre-filter it, and bring it into the plenum. And then you exhaust it. So if 100 CFM is coming from the room, the balance, whether it is 700 CFM to be exhausted, or 800 CFM to be exhausted, or 300 CFM to be exhausted, the balance amount is drawn from nearby adjacent areas which need not be controlled, which need not be tempered, but there's a pre-filter at the entry. The air comes into the supply plenum, comes into the work area after it is filtered, and then is exhausted out. This is how you maintain your air balance. Finally, you have something called Class 3 Biosafety Cabinet, which is almost like an isolator. You have glove ports with gloves. Air coming into the cabinet is HEPA filtered, and the entire air is exhausted out, hard ducted, and with a dedicated exhaust motor blower system. You normally have a pass box on the left. You also have a pass box usually on the right. You have material being passed in from one side and contaminated material being taken out from the other side. It could also feature a formaldehyde or other decontaminating dunk tank built inside this particular glove box. Now here is the comparison of biosafety cabinet characteristics. The BSc class, whether it is class 1 and then class 2, type A1 or B1 or B2 or A2, and finally biosafety class 3. The phase velocity for class 1 and class 2 type A1 is 75. For the others, it is 100. As far as the airflow pattern is concerned, in class 1 cabinet, there is no HEPA filter at the supply. The air comes in at front and is exhausted to the outside or into the room through a HEPA filter, or sometimes, if it is considered not necessary, without a HEPA filter. Now, as I have been repeatedly saying, biosafety cabinets should not be used for work with aggressive chemicals. The materials of construction are not appropriate, are not designed to withstand aggressive chemicals. In type 2A1, the phase velocity is 75, 70% is recirculated, 30% is exhausted, either back into the room or outside, but never hard ducted. You can use the thimble unit or the canopy unit with a 1-inch gap between the exhaust filter and the intake area of the canopy. In the case of class 2 B1, the phase velocity is 100. The airflow pattern is such that there is 30% recirculation and 70% exhaust. And it is through a dedicated duct outside through a HEPA filter. In the case of B2, there is no recirculation. The entry velocity is 100 feet per minute and it is totally exhausted to the outside through a HEPA filter. And in the case of class 2 A2, it is similar to class 2 A1. But the entry velocity is 100 feet per minute and there is no duct which is contaminated and under positive pressure. It's all under negative pressure. The air could be released back into the room after HEPA filtration or could be canopy fitted through a thimble unit to an exhaust duct leading outside. One of the reasons why you find class 2 B1 followed by class 2 B2 and then class 2 A2 is because formally, until the last revision of the NSF standard, this particular configuration was termed as class 2 B3. It has been rechristened as class 2 A2. Finally, you have BSc class 3 biosafety cabinet, where there's no question of any phase velocity because no room air directly enters the cabinet. It is through a HEPA filter and all the air is exhausted outside. In the case of a class 3 biosafety cabinet, it is like a glove box. You have gloves. There's no laboratory air directly entering the workspace or the cabinet. It goes through a HEPA filter. The air going into the cabinet is HEPA filtered and the air coming out is also HEPA filtered. So there's no question of laminarity inside that particular cabinet. The air is bio-clean, but the airflow is not laminar. The important thing is that the inner chamber should be at a pressure differential between the laboratory and the space should be as high as 120 to 125 pascals. Half inch of water pressure is the gradient between the laboratory environment and the workspace within the biosafety cabinet 3. Now, testing, qualifying and certifying biosafety cabinets requires special knowledge. And in the United States, they recognized that there was a shortage of qualified personnel. So, National Sanitation Foundation set up a program in 1993 whereby they offered to train people, test people, oral test, written test, practical tests, and then certify them as accredited qualifiers. Now, as soon as that initiative was launched in 1993, almost all the users across the United States and Canada welcomed it, and all of them insist that whoever comes in to certify their biosafety cabinet is accredited to NSF. And with that encouragement from the industry, today you have, even if your own biological safety officer in-house is to carry out these tests. In other words, if this performance testing and certification is done by a person in-house, that person is encouraged to go for accreditation, and once he is accredited, then he could carry out all these performance tests. Unfortunately, we do not have such an arrangement in India. Now, here's a table that tells you about the tests, the mandatory tests and the optional tests. Now, the mandatory tests are primary containment, the cabinet integrity, HEPA filter leak, downflow velocity, phase velocity of air entering from the laboratory environment into the biosafety cabinet, negative pressure and ventilation rate, airflow, smoke patterns, alarms and interlocks, especially alarms with regard to the exhaust motor blower. The optional tests are for electrical safety in terms of electrical leakage, ground fault interrupter, and so on and so forth. Other optional tests are about the lighting intensity at the workspace, UV intensity, if any UV is being used, though it is not at all necessary in a biosafety cabinet, noise level and vibration. Here's another table for containment tests and the references for each test in the standard, that is NSF 49. You have the HEPA filter leak test, airflow smoke pattern, cabinet integrity, face velocity with the open front, face velocity when the sash is down, the pressure differential, and lastly, the downflow velocity. Please remember that biosafety cabinets are being used by us predominantly to ensure that the air inside is bio-clean and there is both bio-exclusion as well as bio-containment. Now, how do we test it except microbiologically? This entire procedure, the SOP, step by step, is given in NSF 49, which you could download. I only briefly tell you what the process is about. You want to know whether the operator is protected. So how do you know that? You aerosolize a known amount of subtilis from the work area, from the work surface. Let the system be on and try and see whether any subtilis can be recovered where the operator is sitting. The amount you aerosolize should be in the range of 5 to 8 into 10 raised to 8 CFU, and the amount you recover should strictly be nil, but certainly not more than 10 CFU. Now the next thing you'd like to know is my culture protected? So, is the laboratory environment likely to compromise my culture? So how do you know that? So you aerosolize a culture of subtilis from where the operator is sitting and try to see if you can capture the subtilis or recover subtilis at the work surface. The procedure is explained in the standard. Now you aerosolize approximately 5 to 8 into 10 raised to 6 colonies where the operator is sitting and see if you can recover anything at the work surface. Ideally, you should recover nothing, but the limit given to you is 5 CFU. And lastly, you have, depending on whether you're left-handed or right-handed, you have a clean side of the bench and the contaminated side of the bench. Now, you would like to know, you're having laminar airflow. You would like to know whether there's any cross-contamination. So, how would you know that? So, from one side of the work area, you release subtilis and see if anything can be recovered at the other end of the same work surface. Now, the amount you aerosolize is 5 to 8 into 10 raised to 4 CFU of subtilis spores, and ideally you should recover nothing, but the limit given to you is up to 2 CFU. Here's a summary of the requirements at all levels of safety for biosafety cabinets. Biological safety cabinets should not be installed as an integral part of a room supply and exhaust system in such manner that fluctuations of the room supply and exhaust air cause the biological safety cabinets to operate outside their design parameters for containment. It is recommended that biological safety cabinets or fume hoods not be used as the sole source of room exhaust. Room supply air system equipped with dampers to prevent backflow if biological safety cabinets are connected to exhaust ductwork. But it is not good practice to connect the exhaust of biosafety cabinets or fume hoods to the building exhaust ductwork. If biological safety cabinets are connected to exhaust ductwork, connections are by thimble units where appropriate, and room exhaust ducts are equipped with manual dampers to permit sealing for decontamination. Manufacturer's recommendation for installation should be carefully followed. Cabinets to be located away from doors, from windows that can be opened, from room supply air, and from heavily traveled laboratory areas. A minimum of 30 centimeter, approximately 1 foot clearance is recommended where possible behind each side of the cabinet to permit cleaning and testing, and a minimum unobstructed clearance of 40 centimeters at the exhaust filter discharge to permit testing. Biological safety cabinets must be installed and tested in accordance with NSF standard 49. Now here are some cautionary notes. I've been repeatedly saying that biosafety cabinets are not designed for work with volatile chemicals. These chemicals may damage HEPA filters, the risk exposure becomes high, it exposes the personnel if their exhaust is not proper. These BSC fans are not spark proof, they may result in fire or explosion, and never use NFPA for flammables inside a biosafety cabinet. Now, biosafety cabinet exhaust filters, supply filters are all contaminated filters. Before you replace those filters, there has to be adequate decontamination and adequate safety for the person who is making the change of filters, removing the soiled filter and replacing it with a fresh filter. There is a concept called bag in and bag out of HEPA filters that is illustrated here. And this system should be used where possible for removal of filters and replacement with fresh filters, so that the technician changing the filter is not exposed to undue biological or other risk. Now you have something called a performance envelope and nominal set point. Now what is nominal set point? It is determined by the laminar downflow velocity and the intake air velocity. Now, factors that could affect operation airflow balance and cause deviations are variability in instrument calibration, variation in air volume in the laboratory room, line voltage variation, uneven filter loading, and back pressure created by winds if cabinet is vented outside. Now, the consequences of deviation from nominal set point would be that less air is exhausted than designed, less containment capability, and therefore increasing the risk of personnel exposure. If more air is exhausted, contaminated room air may compromise the product. Now, the operating location for BSC, isolated from other work areas, removed from high traffic areas, away from airflow ducts and away from laboratory entry doors. And the operating procedure is load the biosafety cabinet with all needed supplies, turn the biosafety cabinet on and allow to run for 10 to 15 minutes. Check the inward airflow with a piece of tissue. Enter straight into the cabinet and perform work in a slow, methodical manner. At end of work, decontaminate all items to be taken out of the cabinet. Decontaminate the interior of biosafety cabinet. Allow the cabinet to run for 10 to 15 minutes and then shut off. Now this brings us to a very interesting question. If you have a biosafety cabinet, is it okay if you switch it on when required and switch it off when not required? Or should it always be on? The answer can come best in consultation with your engineering department or whoever designed your facility. If the delta P, the negative pressure being maintained in the room, is critical, and that is maintained with part of the room air being directly exhausted out and part of the room air is exhausted through the biosafety cabinets, and that totality of exhaust volume is necessary for the integrity of your pressure gradient, then chances are that you should never ever switch off your biosafety cabinet once it is on. But if your facility does not have any such arrangement, and yours is a standalone biosafety cabinet in a laboratory, and the exhaust from that particular biosafety cabinet is not in any way adversely impacting the delta P, if any, in that laboratory, then you are allowed to switch it on when needed and switch it off. But when you switch it on, wait for 20 minutes for the system to stabilize before you start your work. And similarly, after you've completed your work, wait for 15 to 20 minutes for the system to exhaust out the last bit of contaminants and then is safe enough to be switched off. Otherwise, you might find work surface contamination penetrating the room as soon as you switch off, because the delta P that was being maintained between the laboratory environment and the work surface is now broken. Associated with this is another issue. If in a work-related environment, you're working with a biosafety cabinet and suddenly the power goes off, so the biosafety cabinet is off. I have said that the exhaust should never be off, so it should be through a UPS. But the recirculation that is required or the supply that is required is not there because there is no power supply. Maybe the generator will take over, maybe there is no generator. Now, whatever it is, If you are sitting near the biosafety cabinet and the power goes off, gently turn yourself away, breathe in the other direction, look in the other direction, and don't move unnecessarily. Wait for the power to come. And once the power comes, wait for the system to stabilize for at least 5 to 10 minutes before you resume your work. As I said, the exhaust system is on through a UPS. Therefore, the work surface integrity, the biocleanliness in the work surface will never be compromised. Yet another point to bear in mind is, as long as there is no interference in the airflow pattern, the system will work beautifully. But the moment you put your hands in and you're working, you're disrupting the airflow pattern and you're causing eddies and turbulence. Now you must be very careful to make sure that you don't create so much turbulence that you are permitting part of the work surface air to escape into the laboratory environment. That care you should take, and you should train yourself, cross-check. Smoke testing will help you. Once you are having airflow smoke pattern testing, you put your hands in and see if any of the smoke is coming out into the laboratory environment. This is the best way to check whether your work practices at the workstation is acceptable or not acceptable. Here are some more tips for biosafety cabinet safe operations. Always enter straight into cabinet. Don't make sweeping motions inside the work surface. Place materials well within the cabinet, not near the front grill. Place discard pan within cabinet. Watch for disruptions of laminar airflow. Decontaminate materials before removal from cabinet. It is not designed for chemical use. Do not use it for volatile toxic chemicals. You may, however, use it for non-volatile toxic chemicals or low-level radioactive materials. May use for minute amounts of volatile chemicals. Ensure annual certification. Place all work materials inside the cabinet before starting. Now here are some suggestions for good work layout. A typical layout for working clean to dirty within a class 2 biosafety cabinet. Clean cultures on the left can be inoculated at the center. Contaminated pipettes can be discarded in the shallow pan, and other contaminated materials can be placed in the biohazard bag in the right. This arrangement is reversed for left-handed persons. Now for vacuum. One method to protect the house vacuum system during aspiration of infectious fluids. The left suction flask A is used to collect the contaminated fluids into a suitable decontamination solution. The right flask serves as a fluid overflow collection vessel. A glass plunger in flask B minimizes splatter. An inline HEPA filter C is used to protect the vacuum system D from aerosolized microorganisms. Now here are some tips regarding centrifuges. You have microcentrifuges in the range of 15,000 RPM. You have low or high speeds from 2,000 to 20,000 RPM, and ultracentrifuges beyond 120,000 RPM. The hazards are the mechanical failure of the machine, the lab equipment failure in terms of tubes, etc., aerosol generation, and any errors by the operator. The correct operating procedure would be to check tubes for cracks and chips, use matched sets of tubes, buckets, etc. Tightly seal all tubes and safety cups. Ensure that rotor is locked to spindle and bucket properly seated. Close the lid during operation and allow the system to come to complete stop before opening. Further tips for safe operation: use safety cups whenever possible. Disinfect weekly and after spills or breakages. Lubricate O-rings and rotor threads weekly. Do not use rotors that have been dropped. Contact your centrifuge rep for specific information. As I said earlier, this is just to give you a brief overview. The full text is available in Biosafety in Microbiological and Biomedical Laboratories from NIH CDC 5th edition. Please see that you read it, understand it, and apply it.